Okay, so today we're going to be learning a bunch of different tools that we're going to put in our conversion tool chest here. All right, we learned how to use that constants page to mine that information to get a bunch of conversion factors to convert between units. We're going to learn some very similar tools, but they're going to be much more chemistry relevant, and they all revolve around a particular quantity known as the mole. Okay, so a mole of something is 6.0221 times 10 to the 23rd of that thing, whatever it is that you're talking about. 6.0221 times 10 to the 23, is that a big number or a little number? It's a big number. Not only is it a big number, it's like an incomprehensibly big number, right? It is just absolutely enormous, but that is the consequence of atoms being so small. There are several moles of water in this container right here, right? So on the order of 10 to the 24 water molecules floating around in here. Okay, so this concept of a mole, we're going to make an analogy here. All right, and that is to this quantity that you all know, which is a dozen. If you were to define a dozen of something is simply how many of that thing? How many is a dozen? 12. Right? So in the same way that if I said I had a dozen cookies, everybody would know how many cookies I had. If I said I have a mole of atoms, everybody knows how many atoms I have. I have 6.022 times 10 to the 23 atoms. Okay? Not only that, but we don't have to talk in whole number quantities. I could also say I have a dozen and a half eggs, 1.5 dozen eggs. And again, you might have to do a little math, but you could figure out exactly how many eggs I have, right? So that is what we're going to use this quantity, a mole, for. It's just really to make our lives a little bit more convenient so that when we're talking about chemical reactions, we don't have to talk in quantities as large as 10 to the 23 of atoms, right? Or molecules or whatever it may be. Okay? Before we sort of jump further here, this is going to be a good time to just take a step back and review scientific notation. We've seen it a few times, but now that we're dealing with this quantity, 6.0221 times 10 to the 23, let's just review real quick. Okay. So any number can be put in scientific notation. It was sort of designed because it's a more convenient way to express really, really large or really, really small numbers. Right? So it's a convenient way . If you think back to your frustration with that unit conversion assignment, you had to enter in those really huge numbers in standard notation, right? If we had this convenient way to do it, you wouldn't have to worry about counting your zeros so carefully, okay? The other thing that's nice about scientific notation, and we'll see how it's formatted, is that all of the digits that you see in scientific notation are considered significant digits. All right, so an example of a number in scientific notation would be something like 4.15 times 10 to the 4th. Okay, so this is considered proper scientific notation. There can only be one digit to the left of the decimal. Okay, and again, you just want to kind of convince yourself that because of the format of scientific notation, every number you see is going to be significant because there's always going to be this decimal point in that number. So anything that comes after it is just automatically a significant digit, whether it's a 0 or not. All right, so we want to be able to go from scientific notation into what's called standard notation, which is our normal way of looking at numbers. Okay, so what we're going to do is we're going to take this number, this 4.15, and we're going to multiply it by 10 4 times. All right, and if you can convince yourself with this, with any number in your calculator, the effect of multiplying by 10 is simply to bounce the decimal point over. Okay, now often when we're converting in and out of scientific notation, the question is, okay, well, like which way do I bounce my decimal point, right? And you can kind of have this memorized of left or right or whatever, but the rules change depending on whether you're going into or out of scientific notation. So by far for me, the easiest thing to do is I take a step back and I just ask myself, times 10 to the 4, is that going to be a big number or a little number? A big number. So if I bounce out of scientific notation here, I better be left with a big number. So I'm going to bounce this decimal point over to the right. And I'm going to do so the number of times indicated by my exponent here. 1, 2, 3, 4. Okay, and you see I have these blank spaces here. I'm just going to simply fill those in with zeros. 4, 1, 5, 0, 0, or 41,500. That is the same as 4.15 times 10 to the 4. Okay, so we're going to do our bounce our decimal the number of times that we see in our exponent. All right, so then given that same sort of logic, I want you to take a second and do 3.60 times 10 to the negative 3. All right, big number or a little number? Little number. So now we're going to bounce it the other way, so we get a little number. And I need to bounce it 3 times. 1, 2, 3. All right. So now importantly, this is where my decimal point is going to be located. 0.0036. And what else do I have to do? I have to keep that 0. Remember, my digits that were displayed in scientific notation, that tells me all my sig figs. I need to make sure that when I bounce out of scientific notation, I have that same number of sig figs. Cool? Okay, so then let's just do one. You're going to go in the other direction. 4, 6, 1, 2, 0. 6,120. Take that from standard notation into scientific notation. Okay, so I'm going to have 6.12 times 10 to the something. All right, is my exponent going to be positive or negative? Again, is this a big number or a little number? It's going to be positive because this is a big number, right? Cool, and then I just got to count my decimal point lives over here after the ones place. It's not explicitly written because that 0 isn't significant, right? But that's where it lives. And I'm going to bounce 1, 2, 3. So this would be 6.12 times 10 to the positive 3 in scientific notation. Cool? All right, so You think about it, this number, 6.0221 times 10 to the 23. Now we're talking about 23 bounces of that decimal point to get that number. That's a lot of zeros on the end of that number, right? It's a very large number, okay? Okay, cool. This thing is also what's called Avogadro's number. This is the value that we're always going to use, but let me just show you where you can find it. If we go to our constants page, we'll see we have this entry here that says 1 mole is equal to 6.0221 times 10 to the 23 molecules, okay? I'm going to use a slightly different word here as an example. Okay, so again, we're talking about the mole. We look on our constants page. It says 1, and then the abbreviation for a mole, M-O-L-E, is the abbreviation M-O-L. They really shortened it quite a bit for us, all right? It says that this is equal to 6.0221 times 10 to the 23, all right? It says molecules on our constants page. I'm going to use this word particles here, okay? Because remember, molecules, if we're really being good, correspond specifically to covalent compounds. But I can use this number to talk about individual atoms. I can use this number to talk about ionic compounds, their formula units. You can use this number to talk about eggs if you want, but there has never been that many eggs in the history of the world ever, because that is such an incomprehensibly large number, okay? But particles is kind of this catch-all term. When we use the term particle, that really means anything small. An electron is a particle. There are also dust particles. Dust is a humongous amount larger than an electron, right? So it really is just a catch-all term to mean things that we consider to be small. The other things that you'll see in place of particles here, to be more specific, is our chemistry language here. So you may also see atoms. If you're talking about individual atoms, that's a specific type of particle. Or as it says on the constants page, molecules. And again, if we're really being good for ionic compounds, they're called formula units. Okay. Any one of these terms, when I see it in any sort of a problem, I'm automatically thinking Avogadro's number. And again, that's what we call that 6.0221 times 10 to the 23. Okay? These words should jump out at you as something that's going to require that particular conversion factor, because that's the only way that we have to deal with those individual quantities. All right, cool. So, just like we did with our conversion factors from inches to centimeters, we went and we got that relationship from our table, and then we turned it into something that we can use in our math. And how did we do that? We took this equal sign and did what with it? Yeah, turned it into a fraction. I'm going to stack one side on the other side, all right? And so that's exactly what we're going to do. This is the same thing as 6.0221 times 10 to the 23, that catch-all term particles, over 1 mole. All right, and just like all of our conversion factors, I can use it as is, or I can flip it depending on how I want my units to work out. All right, so this is our form of Avogadro's number we're going to use in our math. All right, so let's take a look at one such problem here. How many aluminum atoms are in 0.675 moles of aluminum? I'm going to start with my given quantity here. I'm going to use my Avogadro's number conversion factor. Am I going to use it as is, or am I going to have to flip it? I want moles on the bottom, right? So I want to use it just as is with the 6.0221 times 10 to the 23. Again, we can be more specific. We're talking about atoms here for this particular problem. So we punch that into our calculator, 4.0649 times 10 to the 23. And then I'm done. Always got to do those two things, right? Really 3 steps. Treat it like a math problem. You need your units, and you need your significant figures, okay? All right, so units-wise, we can see that my moles cancel out, and I'm left with atoms of aluminum. So my units would be atoms. Okay, and then sig figs. Avogadro's number is not exact, but it does have 5 sig figs. Okay, our initial measurement has 3, so we're going to round this thing to 3 sig figs. 4.06 times 10 to the 23rd atoms. Don't chop off that 10 to the 23, right? 4.06 and 4.06 times 10 to the 23 are very different numbers. Cool. All right, so we have this Avogadro's number conversion factor here. This will allow us to go from moles to particles or vice versa. Right, if we had particles to start out with, we would just divide by Avogadro's number to get into moles. Okay, so chemists love moles, and we haven't really talked about chemical reactions yet, but when we do get to chemical reactions, you'll find that chemists love moles because that's how we keep track of chemical reactions. That's how we keep track of how much reactant has turned into product, is by using this quantity moles. Okay? Now, the problem is if you look around this room, this is a nice lab. We don't have a mole counting machine, right? Unfortunately, that thing doesn't exist. If it did, it would make our lives 1,000 times easier. Instead, what we have are the balances, all right? That's how we get a particular amount of a substance, is we go and we mass it out. But then our units are in what? Grams, right? So we need a way to get from grams to moles and moles to grams, and that is this quantity called a molar mass, okay? So if we go to our periodic table, ignore all this. Zoom on into boron here. Okay. We discussed the top number is the atomic number, the number of protons. Then we got the symbol and the name, and then we have this bottom number. And what we've learned about this bottom number so far is that it's an average atomic mass. It's an average of all the different isotopes of boron, factoring in their percent abundance. Okay? It is very much so that. But it is also this quantity known as a molar mass. All right, so I'm going to use boron as an example. Here's that tile from the periodic table. Okay, and we have this 10.811 number down here. Okay, that means that there are 10.811 grams in 1 mole of boron. If you count it out, 6.0221 times 10 to the 23 boron atoms, a mole of boron, and you put it on the balance, the mass would be 10.811. Okay, that's what that number corresponds to. Our units are not just grams, they're not just moles, but grams over mole, or what we say is grams per mole. Okay, so again, we can just make note. the molar mass is quite simply the mass of 1 mole of that substance. Okay, cool. So we need to, again, build a conversion factor from this, right? Again, we're building up our conversion factor tool chest today. We got our Avogadro's number conversion factor. Now we're going to have this molar mass conversion factor. And what we need to do is we need to take this number right here and we need to turn it into something that we can use in our math. All right, and the way we're going to do that is to split up those units. So grams per mole, all written in one line, is the same thing as saying grams over moles as a fraction. Okay, and in particular with this value, this means that there are 10.811 grams in 1 mole of boron. And this is what we're going to use in our math, right? This is what we're going to pay attention to make sure our units cancel out, get us in whatever units that we want. Okay? And again, it's going to play the role of a conversion factor, but not going from, say, inches to centimeters, but going from grams to moles. Okay? The amount that we're going to play this game this semester is going to be just not even fun by the end of it, all right? Hopefully it is. But hopefully it's sort of going to be instinctual how we can do this here, because grams to moles, moles to grams is a game we're going to play over and over and over again, okay? Anytime you see those two same quantities in a problem, your brain should immediately be thinking molar mass. Okay, cool. So I'm going to go to the balance, and I'm going to mass out. All right, I mass out 5.67 grams of boron. How many moles do I have? All right, again, using that molar mass as a conversion factor, we need to convert from grams to moles. Okay, I have my molar mass, 10.811 grams over 1 mole. Am I going to use it as is, or am I going to have to flip it? I need grams on the bottom, and my moles are on top. All right, so that 10.811 grams of boron, I'm going to divide by. That's going to get me in units of moles. All right, 0.524465. Okay. What are my units? Those moles, grams of boron have canceled out, leaving me in moles of boron. And how many sig figs? Okay, so typically we're going to be limited by our measurements, right? We try to use reference values that have a lot of significant figures so that they're not what limits us, okay? But importantly, we do have this distinction between our exact conversion factors and the ones that are not. And molar masses are not exact, okay? So we do have to still look at our molar mass. Typically, we're not limited by them. Our periodic table tries to give us as many digits as possible, but it's like limited to the accuracy of whoever took those measurements, okay? So in this case, my final answer would have 3 significant figures, or 0.524 moles of that boron. you have a question?
But the balances go to how many?
Our balances really go to 4 decimal places. You're right, this was not a great, I was using some other crappier balance that was way cheaper. Okay. All right, so that's all well and good if we're talking about individual elements. All you got to do, if you're talking about carbon atoms, you just go to the periodic table and you look it up for carbon. If you're talking about aluminum, go look it up for aluminum, right? But often we're not just talking about individual elements, we're talking about compounds. Okay. All right, and we're going to, so let's just think about this real quick. If I have 1 molecule of CO2, everybody take a second and tell me how many carbon atoms and how many oxygen atoms I would have. Okay, nothing too crazy, right? 1 molecule of CO2 means that I have how many carbon atoms? 1. And how many oxygen atoms? And again, that's just the definition of my molecular formula here. That 1 is that missing subscript next to the carbon, and that 2 is that subscript next to the oxygen, right? That's where you got those numbers from. Cool. All right, well, what if I have 1 dozen CO2 molecules? I want to know how many dozen of carbon atoms and how many dozen oxygen atoms I have. Not the total number of atoms, but how many dozens of atoms do I have? All right, if I have 1 dozen CO2s, that'd be 12 of them. There'd be 12 carbons, which is a dozen. So again, 1 dozen carbon atoms, and how many dozen oxygen atoms? 2. Okay? And remember, our analogy here with our mole is just the same as a dozen. It's just specifying a particular amount. So if I have 1 mole of CO2, that means I have 1 mole of carbon and 2 moles of oxygen atoms. Right? And it's a little bit weird because we're talking about this humongous number, 6.022. But again, if you can convince yourself that this is true for a dozen, a mole is just the same analogy, right? It's a specific number of those CO2 molecules. Again, I'm just getting these numbers straight from my chemical formula. Okay, so that means that the molar mass of that compound is going to be the molar mass of carbon plus 2 times the molar mass of oxygen, right? I just need to add everything up here. Okay, so the molar mass, what we abbreviate as these big capital M's, of my carbon dioxide is just equal to the molar mass of carbon plus 2 times the molar mass of oxygen. All right, the values straight from the periodic table, which I should probably get. Okay, when we go to calculate this carbon dioxide molar mass here, it's an addition problem. So does that mean I have my position sig figs or my counting sig figs? Position. And if we look on the periodic table, all these elements have a different number of decimal places, making carrying your sig figs a huge pain in the butt for molar masses. All right? So I'm going to make you a deal. We're just always going to use every digit on the on the periodic table, and then we can just go ahead and trust the number on our calculator. All right? We're going to make it easy for ourselves here. Okay? But you have to use every digit from the periodic table. If we look at oxygen, for example, its molar mass is 15.9994. That number is very close to 16, but it is not 16. It is 15.9994, right? Just going to use all the digits from your periodic table all the time, okay? And then we won't worry about keeping track of our addition sig figs. Is that a deal? Cool. All right, so everybody take a second and give me the molar mass of carbon dioxide then. That's carbon. Now you got to add the 2 oxygens. Okay, so the molar mass of CO2, punch that into my calculator, 44.0095. And what are my units there? Grams per mole, right? Not just grams, but grams per mole. Okay. All right, so everybody take a second. Turn this into our conversion factor that we're going to use in our math. Right? How do you set up that term as it will appear in your math? All right, that's the 44.0095 grams that are in 1 mole. Okay. Importantly, those are the units, grams and mole. It's also not a bad idea to keep track of who you're talking about, but the CO2 is really just like a helpful note for you. The units are the grams and the moles. Okay. All right, cool. So we would use this as our conversion factor to get from grams to moles or moles to grams, just like we did in the previous problem. All right. But now we're going to try to do something a little bit more difficult here, and that is to combine what we learned about Avogadro's number with what we know about molar mass. Okay? One of the more challenging aspects of all these conversion factors that we're going to be building here are not using it in like a one-step problem, but having a multi-step problem that you need to use multiple of these conversion factors. Okay? So let's do an example here. We can use that same compound, carbon dioxide, that we just calculated its molar mass for. And I want to know what is the mass of 6.79 times 10 to the 24 CO2 molecules. Okay, let's see if we can plan this out here. What are our units that we're starting in? So we got molecules, and we need to go to units of mass, which is going to be what? Grams. Do we have any way to jump from molecules to grams in one step? Okay, all right. Well, we're not going to be able to do this in one then. But let's think about it. This word molecules, out of our tools in our conversion tool chest, what do we have that deals with molecules? Avogadro's number. And again, that is the only one that deals with that particular set of units, right? So that needs to jump out as being our first step. Okay? And if we use Avogadro's number, where will we be units-wise? Moles. That will take me from molecules to moles. Do we have a way of getting from moles to grams? What do we do? What do we have that will do that for us? Our molar mass. Awesome. Okay, so we need to go from molecules to grams, and we're going to do it by first using Avogadro's number to jump into moles, and then we'll use our molar mass to get from moles to grams. All right, so starting this off, 6.79 times 10 to the 24 molecules. Okay, I'm going to have to divide by Avogadro's number. That's 6.0221 times 10 to the 23 are in 1 mole of CO2. Okay. I want everybody to take a second and look at their calculator answer real quick. If you got some ridiculously large number, like 4.96 times 10 to the 40th or something like that, the problem was the way that you punch that into your calculator, because we're going to be dividing by a number in scientific notation, and if you're not careful, you're going to mess up your order of operations. We need to keep the 6.0221 and the times 10 to the 23 in the denominator of this fraction. So when you punch it into your calculator, you need to put that in parentheses, all right? Anytime you're dividing by a number in scientific notation, you kind of got to be careful, and the safest thing to do is to throw it in parentheses, right? That'll make sure that it all stays together underneath your divisor sign. All right, cool. So now I'm in moles of CO2. I just need one more jump. Moles of CO2 to grams. That's that 44.0095 value we calculated earlier. Okay, so punch that into my calculator. First do the math. I get 496.22136. Okay. You notice that I always just put down a bunch of extra digits. I'm just trying to make sure I have a few extra beyond where the actual significant figure is in this number. Okay? That's a really good habit to get into, and when we're doing our calculations in lab, we're going to use that same sort of practice of copying down a bunch of extra numbers and marking our sig fig with the bar. I guess the bottom line being is if you round it off right here from your calculator and put that in your notes, and you rounded wrong or you did a calculation error, all of a sudden you can't check that quite as easily. Okay, what are my units? Grams of CO2. So the units are grams, and then how many significant figures? 496 grams of CO2. Cool. Okay, one more of these conversion factors to go here. This is what's called a mole ratio. All right, so let's remember what we established when we were talking about molar masses, that if we had 1 mole of carbon dioxide, it would consist of 1 mole of carbon atoms and 2 moles of oxygen atoms. Okay. Again, those numbers just come straight from our formula here, from our subscripts of our chemical formula. We can take this same information and build what's called a mole ratio. The ratio of moles of oxygen to moles of carbon dioxide. All right, and just like we established up here, there are 2 moles of oxygen for every 1 mole of carbon dioxide. What if I wanted to build a conversion factor from moles carbon to moles carbon dioxide? Yep. Boom. Again, straight from our chemical formula. Okay. One important note about mole ratios. Mole ratios are exact. Okay, so what do I mean by exact? Are those going to limit our sig figs, or do we get to ignore them? We get to ignore them, right? So these will never limit your sig figs. Okay, so then using this example here, let's see if we can't put our mole ratio into action here. How many moles of CO2 contain 16.36 moles of oxygen? All right. I'm going to start out with my 16.36 moles of oxygen. And here it's going to be really important to keep track of who you're talking about. So I don't want to just write moles, I want to write moles of oxygen. All right. If I look up at these 2 conversion factors at the top of the screen, which one am I going to use? The one on the left or the one on the right? The one on the left, that's going to be, that's the one that contains my units, moles oxygen. And I'm going to have to divide by that mole ratio, or flip my conversion factor, such that moles oxygen are on the bottom and moles of carbon dioxide are on the top. All right? So if I have 16.36 moles of oxygen, I have half that many, or 8.18 moles of carbon dioxide. Okay? Am I done? That was step 1, the math. What about step 2? Units, and my units are moles, specifically moles of CO2. And so is that my final answer? What's it missing? Sig figs. Started out with 4 sig figs, and again, those mole ratios are exact. So I have to round my final answer here to 4 sig figs as well. How do I do so? I'm just need to tack a 0 onto the end there. Yep. Cool. Final answer. Okay, so let's kind of put into practice everything that we did here. Okay. All right, so we got 4.223 times 10 to the 23 times 10 to the 22, sorry, molecules of water. All right, and you're going to tell me the following quantities. Moles of water, grams of water, and finally moles of hydrogen. I'm gonna quietly sort of start filling in up here. So if you're stuck, look up. Okay, so in order to get to moles of water, I'm going to divide by Avogadro's number. Again, make sure to put it in parentheses in your calculator or you'll get some really, really large number like times 10 to the 45. Okay, that will put me in moles, and then I'm going to look for my sig figs. I got 4 to start out with, and Avogadro's number has 5. Okay. So my final answer rounded to my correct number of sig figs, 0.07013 moles of water. Boom. Okay. How am I going to get to grams of water? What am I going to have to use? Molar mass. Okay, so first thing you would have had to have done is gone to your periodic table. Okay, the molar mass of water would be 2 times the molar mass of hydrogen plus the molar mass of oxygen, which works out to be 18.01528. Again, we're just going to take all the digits, grams per mole. Okay. Since I previously calculated the number of moles of water, I can use that value. Importantly, you're not going to use your rounded value, right? I'm going to make sure to, what I'm practically going to do is go up and copy it on my calculator so that it carries all those digits. But on paper, I'll be good and use my number that has a bunch of extra digits and the sig fig marked. Okay. Am I going to be multiplying or dividing by that 18 value? Okay, I need moles on the bottom and grams on the top. So that 18.01528, that's how many grams are in 1 mole. So punch that into my calculator. 1.26333. And now I have grams of water. Again, I'm going to have to round this to my 4 sig figs. 1.263 grams. Boom. Cool. So Avogadro's number got us to moles. Molar mass got us to grams, and what are we going to use to get to moles of hydrogen? That mole ratio, right? So I need to use that mole ratio that tells me there's 2 moles of H for every 1 mole of H2O. So again, I can start with my moles that I calculated from part A here. I'm going to be good since we're using a mole ratio and make sure to label this moles H2O. And then I'm going to use the mole ratio. For every one H2O, there are 2 hydrogens. So I'm going to multiply that value by 2. We get 0.140250. And that's moles of hydrogen. Again, rounding to my 4 sig figs, 0.1403. Cool. All right, so these were our conversion factors that we learned about today. In our first example, we have Avogadro's number. That's what we started out with. That allows us to go from moles to particles, whether those particles are atoms or molecules. Then we used our molar mass. That was the second one we learned how to use, getting us from grams to moles or moles to gram. And then finally that mole ratio. Okay? So again, we need to be able to use these, but also to sort of mix and match here. All right, so now let's throw in some of our other quantities that we talked about here. All right. So water, we're going to use density. I want to know how many moles of water are in 765 milliliters. And then we're also going to put down a worst case scenario one here. All right, let's go for it. Let's try to map this first one out here. Where are we starting units-wise in this problem?
765 volts.
Our milliliters. So we have our volume. Okay. And what are we trying to get to at the end of this problem? How many moles of water? Okay. Okay, we have no way of jumping from milliliters to moles directly. Okay. We know how to get from particles or water molecules to moles or grams to moles, but we can't get from volume to moles in just one shot here. All right? So importantly, the other piece of information that's given is the density of this liquid, the density of water. And the density is how we can go from milliliters to what units? Well, to grams. There we go. Okay. If you just look at the units for density, grams per milliliter, that's a conversion factor that we can use to go from grams to milliliters or milliliters to grams. And once we're in grams, then we can use our molar mass. Okay, so now importantly, we did this with our molar mass before. All right, but I think the first step here that you need to be able to see that you can do, or else it's really hard to understand how to use that density information, is to turn this into something that we can use in our math. And just like with our molar mass, how did we do it? We split up those units, grams over milliliters, right? So that 0.998 grams per milliliter, that's the same thing as saying there are 0.998 grams in 1 milliliter, right? So just like we turned our molar masses into a conversion factor, we want to do the same thing with our density. Okay, so starting out with that 765 milliliters, I'm going to multiply by my density such that milliliters are on the bottom. Okay, if I stopped here, I would have how many grams of water, but I wanted to jump to moles, so I'm going to use that molar mass. We calculated that value earlier in a previous problem, 18.01528 grams of water in 1 mole of water. Okay, so punch this into our calculator. That 765 mils is 42.3790 moles of water. And then I'm going to do my sig figs. Both my milliliters and my density have 3. That's going to limit me to 3. Okay, so 42.4 moles. Boom. All right. So this one's kind of worst case scenario here. Okay. First of all, there's a few things that we got to be able to do. Not only is it a multi-step conversion, but I also have to know what the heck I'm talking about here. Aluminum oxide, right? This is what we would have learned how to do last week to go from the name of an ionic compound to its formula. Okay, aluminum oxide, when we're putting our formulas together here, what do we always say? It's all about the charges. So I need to look at the charge of an aluminum ion and the charge of an oxide ion. An aluminum ion has what charge? +3. And what about oxygen? -2. And then we do our swap, right? So aluminum oxide is Al2O3. Okay, cool. All right, so now let's try to build a map here. We're trying to go from pounds all the way to moles, and not just moles, but moles what? Oh, my bad, not moles. Not just atoms, but atoms of aluminum, specifically. Okay. So, maybe you don't see the direct path forward, but let's start thinking of what our tools are here, and maybe we can bridge this gap, okay? So first of all, atoms of aluminum. What do I know I'm going to have to use if at the end I want to get to atoms of aluminum? Avogadro's number, all right? So we're going to work backwards here. And if I use Avogadro's number, what units must I have started out with? Moles, and not just moles, but moles of aluminum. All right, let's be good here. Our pounds that we're given in our problem, is that pounds of aluminum? It's pounds of aluminum oxide. All right, so we need to get to moles of aluminum, but we're starting out in this quantity of aluminum oxide here. Okay, so now let's think about it. We're given pounds. Do we like to work with pounds in the science classroom? No. So what are we going to convert that mass to, which is going to be way more useful in a science classroom? Grams. Okay, and we can do that. That's just one of our unit conversions. Doesn't matter what we're talking about, we can get from pounds to grams. In this case, though, it would be aluminum oxide. And now I see grams and moles in the same problem here. So what am I automatically thinking? Molar mass. All right, but importantly, if I have grams of aluminum oxide, I'm going to need to use the molar mass of aluminum oxide. And if I use the molar mass of aluminum oxide, that will put me in moles of not aluminum, aluminum oxide. Now I got one more jump to go here. How can I get from moles of aluminum oxide to moles of just aluminum? The mole ratio. All right. So just setting it all up here, 4.5 pounds. Again, we'll be good and keep track of who, aluminum oxide. We're going to need to find our pounds to grams conversion factor on our chart, right? This tells us that there are 453.59 grams in 1 pound. Okay, now that I'm in grams of aluminum oxide, I'm going to use my molar mass. I had to calculate that from the periodic table. That's 101.973276 grams of aluminum oxide in 1 mole of aluminum oxide. And then the one that is the most deceptively simple to set up, and yet people tend to forget about it the most, the mole ratio. This will allow me to go from my 1 mole of aluminum oxide, which contains 2 moles of aluminum. Okay, and if I stopped there, I would have my units be moles aluminum, but I'm going to make that one more step. 6.0221 times 10 to the 23 atoms. Okay, punch this into my calculator. I get 2.4108 times 10 to the 25. That's aluminum atoms. I'll round that to my 2 sig figs. 2.4 times 10 to the 25 aluminum atoms. Boom. Cool. Right, so we talked about unit conversions actually the very first week, and then we introduced these three new conversion factors that are very chemistry specific. Again, when we start talking about chemical reactions, we'll be doing so in moles. So it's not really a unit that you see outside of chemistry, but we love it in chemistry, all right? We have our molar masses to get from grams to moles. We have mole ratios, as well as Avogadro's number. Cool. And again, the challenge is going to be the mixing and matching, such like in these last two problems here. Break.